Hello everyone, welcome back to Math 1314, more on math. Today we're going to talk about Chapter 4, Section 5. Section 5 deals with rational functions. Remember, rationals mean fractions. Our objectives today is we're going to find the domains of these functions and we're going to graph them. And look at their graphs. We're going to identify all the asymptotes. There are three types. There's vertical, there's a horizontal, and there's an oblique. And then we're going to solve some problems. Alright? First off, there's a note. The quotient of two polynomials is not itself a polynomial. For example, if we had 2x plus 6 over x plus 3, we know we can factor out a 2 in the top one, leaving us x plus 3, and the bottom is x plus 3, so they cancel. So it's not necessarily a polynomial. In this case, it's a monomial. Alright. Rational functions. Let's talk about those. A quotient of two polynomials looks like this. We have a function, so we have one polynomial divided by another. The domain of f of x are all x's that does not make the denominator equal 0. So at the bottom, reason being, if we have 0 on top, 2 goes into 0 no times. But 0 goes into 2 infinite times, so it's undefined. So we cannot have a 0 on the bottom. We talked about this earlier in the class. Actually, we did some of these in the beginning part of Chapter 2 in transformations. Tell me the domain and graph the function. Actually, in the past we saw, okay, if we look at this basic function, it looks like 1 over x. Push the number stays together. So since it's 1 over x, from our library of functions, we know the graph looks like this. Then we notice that the bottom shifted. If we took the bottom, set it equal to 0, we get x equals 3. So that's our new asymptote. The graph looks the same. That's a new vertical axis. So this is exactly what we looked at. So in other words, since we cannot have 0 on the bottom, if x equals 0, if x equals 3, then we have 0. So our domain here, it goes from negative infinity all the way to positive 3, and then starts again at positive 3, and then goes on to positive infinity. And there's our graph of it. Alright, so let's look at some more examples on this. This is basically what we're looking at. Is we've done it before, now we're going to have some names for it. So the domain is all x's except where denominator equals 0. That's how you find the domains of a function, of a rational function. So here we have the first one, 1 over x. Set the bottom equal to 0, so our domain is from negative infinity to 0, 0 to positive infinity, because that's the only x I cannot use. Again, take the bottom, set it equal to 0. So x cannot be 0. It's also the same. Let's look at this one. So, since this is a quadratic equation, the first thing we have to do is factor the denominator. Factor both numerator and denominator. We'll eventually use this later. So, our denominator, x squared minus x minus 2, that goes in the first spots. Opposite signs, so one's positive, one's negative. The bigger number gets negative. So what times what is 2? When you subtract them, you get 1, 2, 1. And again, the 2 gets the negative sign gets a 2. And the top number is already factored out, so we'll talk about him later. So we set these equal to 0. So we get negative 1 and 2. So, I'm sorry. X plus 1 equals 0. X minus 2 equals 0. So these are the two values I cannot use because they make the bottom equal 0. So my domain is from negative infinity to negative 1, from negative 1 to 2, and then from 2 to positive infinity. Because if you look at it, we have it at negative 1 and at 2. So we can't use that value, we can't use that value. So here's 1, 2, 3 segments. Alright, let's look at another one. (2x plus 5) equal over 2x minus 6. The top can't go any further, but the bottom we can factor out of 2. And whenever you factor out of 2, or anything, to figure out what was inside. So these two cancel, we have x. 6 divided by 2 is 3. 2 can't go anywhere, can't do anything, so the only thing I set equal to 0 is x minus 3. So the only x I cannot use is negative 3. So my domain is from negative infinity to 3, and then from 3 to positive infinity, because that's the only number I can't use. So yeah, it's no matter how big or how small the equations are, it's the same process. So I've got to factor out the numerator and the denominator since they're both quadratics. So we have x, opposite signs. The bigger number gets the plus. So what times what is 3? When you subtract them, you get 2. 3 and 1. 3 times 1 is 3. 3 minus 1 is 2. And the plus gets the 3. Same thing down here. Opposite signs, one's plus, one's minus. The bigger number gets a minus. What times what is 2? When you subtract them, you get 1. 2 and 1. Set the bottom parts equal to 0. So x cannot equal negative 1, and x cannot equal 2. Because if I plug those in there, I get 0 on the bottom. So my domain is from negative infinity to negative 1, negative 1 to 2, between there, and then from 2 to positive infinity. And the last one. This is ready. Alright, so we set the bottom equal to 0. So x equals negative 1. X cannot equal negative 1. So my domain is from negative infinity to negative 1, negative 1 to positive infinity. So that's how we figure out our domains. This leads us to this discussion of asymptotes. Asymptotes are restrictions to the values of a function. The first one we're going to talk about is a vertical asymptote. The vertical asymptote, any x value that makes the function undefined. In other words, makes the denominator equal to 0, which we just found those up top. Those are all vertical asymptotes that we've discussed. So the vertical asymptote of this one is x equals negative 1. That's the vertical asymptote because you cannot use it. If you can't use it, those are the vertical asymptotes. Just a couple of examples here. Find the vertical asymptotes. Two x minus 11, x squared plus 2x minus 8. The vertical asymptote. You can have none, you can have one, you can have a whole bunch of them. So in this case, since it's a quadratic equation, we have to factor out the bottom. So it's x and x. Second sign's a minus, so it's opposite signs. What times what is 8? When you subtract them, you get 2. 4 times 2. 4 minus 2 is 2. The bigger number gets, so the 4 gets the plus. Set those equal to 0. So x equals -4 and x equals 2. Since I can't use those, then my vertical asymptotes are x equals -4, x equals 2. Whatever I can't use, that's my vertical asymptote. So, these are both polynomials. This one, they both have an x in common. So they both have an x. I think I have an x. I have x minus 4 left. They both have an x. Remember, when I factor something out, I divide. So this is going to be x squared minus 1. This is still quadratic, so I see if I can go any further. And I can because it's a difference of 2 squares. So it's x plus 1, x minus 1. These x's cancel. Even though at this stage, x equals 0, I can't use 0. X plus 1, so x equals -1. I can't use -1. And I can't use +1. It'll make that so. My vertical asymptotes are 0, 1, -1. Even though, now, because this disappears, if there is a common factor in both the numerator, that's the top number, and the denominator, that's the bottom. If there's a common factor in both denominators, then that 0 value becomes a hole in the graph at that x value. Alright, so if, like here, the x is cancelled, so at 0, it's my graph, let's say this is my graph. Instead of like this, I would have a hole, an open spot there. Alright. And one more. X cubed minus 5x. Okay, the top is linear already, so leave it alone. The bottom has one x in common, so I take out one x out of both of them. I set them equal to 0. So x equals 0. That's an asymptote. X squared minus 5 equals 0. So x squared equals 5. Square root both sides. X equals plus or minus radical 5. So my vertical asymptotes here, x equals 0, positive radical 5, and negative radical 5. Those are my vertical asymptotes. Now the second type we're going to look at is a horizontal asymptote. So if we look at any polynomial, we have, so f of x equals p of x over q of x. A sub n, x to the power n, a sub n minus 1, x to n. So this is a standard way of looking at polynomials. A sub 1 x, a sub 0. And the bottom, b sub n m. B sub m minus 1, x sub m minus 1. B sub 1 x, b sub 0. So I have to make sure I differentiate the coefficients and the exponents, and so the n's on top, m's on the bottom. The shape of a polynomial depends greatly on the leading term. So what we have to look at then all we have to concentrate on is the leading term. This will define our horizontal asymptote. Three conditions. Looking at the exponents. If the top is bigger than the bottom, if the top exponent is bigger than the bottom exponent. Okay, what happens here, the horizontal asymptote does not exist. It goes to infinity. Let's see what this means. So if I had 2x to the 5th over 3x to the 2nd. Remember, we're always looking at, as x goes to infinity, what happens to the graph. So since there's more x's on top, I subtract them. So now what happens to this graph? It goes to infinity. So there's no horizontal asymptote. So no horizontal asymptote. If the top is bigger than the bottom, let's see if they're equal. If the exponents are equal, these are exponents of x. The horizontal asymptote is simply the coefficients. Two x to the third over 3x to the third. Since they're the same, they cancel out. We're left with 2 over 3, which is the leading coefficients. And if the top is less than the bottom, the horizontal asymptote is 0. Two x to the third over 3x to the fifth. This is 3, this is 5. So I have more on the bottom. Remember, as x goes to infinity, one over x. Remember what the graph looks like this way. As x goes to infinity, it gets really, really close to 0. If I have 1 over x squared, it goes to 0 a lot faster, or close to 0. So as x gets larger, this number gets smaller, smaller, smaller. Eventually, it gets very close to 0. So if the top exponent is smaller than the bottom, horizontal asymptote is 0. If they're equal, it's simply the coefficients. If the top is bigger, there is none. There's no horizontal asymptote. All right, let's look at some examples here. Find the horizontal asymptotes. The first one, 1 over x minus 3. So what happens next? The top one, since there is none, it's x to the 0. On the bottom, it's x to the 1. Remember, so this is n, and this is m. N is less than m. If n is less than m, then the horizontal asymptote is 0. So the horizontal asymptote is 0. The horizontal, so this is y0, or the x axis. So the horizontal asymptote finds the y value. All right, let's look at another example. -7 x to the 4th minus 10x squared plus 1, 11 x to the 4th plus x minus 2. Remember, we only look at the leading terms, so we're only paying attention to this. This is n, this is m. Since n equals m, the horizontal asymptote is simply the coefficients. Two x plus 3 over x cubed minus 2x squared plus 4. I only look at the leading terms, so I have 2x over, so this is first, that's third. So this is n, this is m. N is less than m. Whenever the top is smaller than the bottom, the horizontal asymptote is 0, or the x-axis. Alright, so again, in this one, we want to look at the leading terms. So we have 2x squared over x squared. Since they're the same, this is n, this is m. So that since they're equal, they cancel out. The horizontal asymptote is 2 over 1, which is 2. 1, 2. So with this one, you know the horizontal asymptote is 2. The vertical asymptote is 0. So the graph looks like this. What we would do is plug in some points. 1x is 1. 2 plus 1 is 2 over 1. X is 1. That's 3. So yeah, so when x is 1, y is 3. So that's pretty much how you look at horizontal and vertical asymptotes. But there is one but. Has to do with the horizontal asymptotes. If n plus 1, well, no, n equals m plus 1. In other words, if the top exponent is bigger than the bottom exponent, then we have, so notice, if we had x4 over x3, as we said earlier, if the top exponent is bigger than the bottom, then there's no horizontal asymptote. But there's always a but. If there's a difference of 1, so these cancel, so we just have x. Then we have an oblique asymptote. Oblique slant. So, normally, if the top is bigger than the bottom, then we have no horizontal asymptote, unless the top is bigger than the bottom by 1. If we have that, then we have an oblique or a slant asymptote. To find the oblique asymptote, we must perform long division to find the equation of the asymptote, of the oblique asymptote. The oblique asymptote. So, here's an example. Two x squared minus 3x minus 1 over x minus 2. Right, we don't have a horizontal asymptote because the top's bigger than the bottom, but since it's bigger than the bottom by 1, we have an oblique asymptote. So we have to do long division. What times x gives me 2x squared? 2x. 2x times x is 2x squared. 2x times negative 2 is negative 4x. Change the signs. So 4 minus 3 is 1x, and bring down. What times x is x? They're both positive, so it's positive 1. 1 times x is x. Negative 2. Change the signs. It doesn't matter what that is, because once we have a linear equation, that is the equation of our oblique asymptote. So now we talked about our horizontal, our vertical, and our oblique asymptotes. So note here, make sure that there can only be one horizontal asymptote or one oblique asymptote. You cannot have them both. All right, so end of part 1. Part 2 is going to be examples of how to use all this stuff to start graphing polynomials.